Ladies and gentlemen, for joining us today. This is our third webinar in our 4-webinar series on high-purity water treatment. I'm going to go over some housekeeping issues for you real quick. This is recorded and will be available for download at a later time. We'll have a Q&A session at the end of the event, so if you could put your questions in the Q&A section and we'll answer them. I'll read them and David will answer them. Really quick, for those of you who may not know anything about Yokogawa, I wanted to give a brief overview of who we are as a company. Our goal is to contribute to society through brand-raising activities in areas of measurementation, control, and information. And individually, we aim to combine good citizenship with the courage to innovate. We started in 1915, and we operate in 33 different countries through 85 different companies. Within the North America, we have 4 headquartered offices, one in Calgary, Canada, one here in Newnan, Georgia, just south of Atlanta, one in Sugar Land, Texas, and one in Mexico City. Just of the U.S. alone, we have sales offices and people in your backyard all over the U.S., same thing for Canada and Mexico. From control and safety systems to your field instruments, your pressure, your temperature transmitters, to your data acquisition and your recorders, to your rollers, to gas analytical, your GCs, your zirconia, oxygen, to your liquid analytical, conductivity, pH, dissolved oxygen. We also have a system integration group that builds sample systems called measurementation. We have a semiconductor division. We also have a test and measurement division. And we have a meters with handhelds for your calibrators or your insulators. We have a life science division as well. I want to thank everybody for joining us today and do a little introduction. Our guest speaker today is David Paul. He is the president of David H. Paul, which is a high-tech water treatment training and consulting firm located in the U.S. David has over 37 years of experience in membrane and high-purity water treatment and over 26 years of training and consulting in these areas. He has trained and consulted at hundreds of plants around the world. He has published over 160 technical articles and papers, and he holds a BS degree in biology and an MS degree in microbiology. So without further ado, I want to go ahead and pass the presenter ball to our guest speaker, David H. Paul, and welcome him for joining us today. Thank you very much. And you should have the ball now, David, and we see a gray screen at the moment. And we have a PowerPoint presentation. Thank you very much.
Thank you, Lynn, and hi, everybody. Thanks for taking the time to watch this webinar, be with us today. In case you don't know about David H. Paul, Inc., we've been doing high-tech water treatment training since 1988. High-tech means basically anything that's not conventional water treatment. So lots of different technologies we train on, and in lots of different formats, from online to classroom to hands-on training at facilities or yours. We also do troubleshooting consulting and other forms of consulting as well. So this is part of a 4-webinar series. First webinar was an overview of high purity water treatment. The second one, we focused on monitoring RO units. Now, each one of these webinars had a little different name, but the nutshell is what the main focus was. So the second webinar, monitoring RO units. This webinar is monitoring RO pretreatment, and the next one will be monitoring high purity water. So same time, number 4 will be the same time 2 weeks from now. But we're focusing on RO water treatment today. So just as a brief review from the last 2 webinars, we saw that in today's high purity water treatment systems, there typically is an RO treatment step. In this case, we're just showing an RO unit. And the RO unit is what is removing the bulk of the dissolved and suspended contaminants. But the unit can have problems like scaling, fouling, and chemical attack. So we have to protect the RO unit from those 3 problems, and that's called pretreatment. So pieces of equipment, the treatment steps ahead of RO unit are called pretreatment. They're to protect the RO unit from scaling, fouling, and chemical attack. And then if the RO permeate, the water that passes through the membrane, doesn't meet end-use requirements, then we have to polish it to meet end-use requirements. And that is going to be the focus of the next webinar. we spoke previously in the two webinars about scaling, fouling, and chemical attack being potential RO problems. We also webinar a good portion of the time on monitoring our units. We're going to monitor normalized permeate flow and it'll drop for both scaling and fouling. I'm just giving an example here. If you want more information, go back to the previous webinar. We talked about monitoring normalized pressure drop or simply pressure drop of each stage. Scaling is more first stage, scaling more second stage. And then normalized salt passage, which tells us the status of the drain, if it's able to reject well or not. In this case, the salt passage is going up, and so there's a problem. Today, I'll just go an introduction on RO pretreatment, and then we're going to go monitoring for scaling control, monitoring for fouling control, and monitoring for chemical attack control. So RO pretreatment is scaling control, fouling control, and chemical attack control, because the purpose of the pretreatment is to protect the RO unit from scaling, fouling, and chemical attack. So if you have a problem in an RO unit, you can't put the blinders on and just look at the RO unit. If the unit is having a scaling, fouling, or chemical attack problem, then the pretreatment control really needs to be looked at, and that's the purpose of today. So doing this monitoring, we would love to see normalized permeate flow as a straight line. That is that today, the RO is operating the same as when it was new and clean and everything was perfect. Whatever it looks like that, never is a straight line. It looks more like this. So in this case, we're seeing that yes, the performance is dropping, the normalized permeate flow drops, but then we do a chemical cleaning and bring it back. So this is the straight line in this case is kind of jagged as and or scaling occur, and then you clean it. Same thing with pressure drops. We'd love to see straight lines, but that's usually not the case. And in this particular case, we're seeing that cleanings have some impact, brings back to new performance, but something is really, really wrong with this system because we're not able to clean it back to performance. Again, chemical attack control. For normalized salt passage, we would love to see a straight line, but in this particular plant, this was the straight line, or almost straight line. So the real world monitoring doesn't give you lines. At scaling, what are the common pretreatments today for controlling scaling? Action is one, scale inhibitor injection is the most common, and softening is the third. So let's just do a couple of slides on each one of these. Acid injection or a polyamide thin film composite membrane is only for carbonate scale control. For the few that may have cellulose acetate membrane, it's very common that you have to inject acid because you have to have the pH in around 5.5 range as the membrane itself is hydrolyzed. Most common, over 99% of all the membranes we're going to run into are going to be polyamide thin film. If you're injecting acid, you're injecting it for carbonate scale control. The reason that we want to do the monitoring and make sure that the acid is being injected properly is we want to make sure that that pH doesn't get back. Because if we higher pH than we actually want, that's going to increase the calcium carbonate scaling potential. That's why we're injecting acid, to get rid of the carbonate so you don't have calcium carbonate scaling. So we're going to monitor the pH with Upstream instruments and also verify the accuracy of the on-stream using calibrated handheld instruments. So acid injection is not so common and for carbonate. if you have more than a carbonate scaling potential, you're going to have to use either scalar injection or softening. In this case, we're talking about inhibitor injection. So basically, chemistry is well known, the scaling is well known, and there are many products that you can use to control scaling of basically any scaling compound. But they only work to a certain level. So they'll work to a certain percent saturation. So if you had scale inhibitor, then 100% saturation would be the absolute max. Well, by scale inhibitor, like for sulfate, maybe you can go to 250 or 300% saturation. But it still won't protect you if you went to 400 or 500% saturation. So as far as monitoring, we want to make sure that the dosage is correct, that we're not adding too little. If we add too much, it's going to hurt our pocketbook. It probably won't hurt anything else. So the monitoring for scale inhibitor dosage is a drawdown test where you have a graduated cylinder. You graduated cylinder from the tank and then close the tank valve, and now you're sucking out of the graduated cylinder, and you can figure out how many milliliters per minute you're injecting, and based on the flow rate to the RO unit, then you can determine the dosage. So that's the best way for an injection. The last three is softening, and softeners, so everybody's heard of home water softeners. In the old, they were called sodium zeolite softeners. These are an exchange, so have little beads, little ion resin beads, and in this, you're exchanging the scale-forming double-charged cations, those are the positively charged ions, and replacing them with non-scale-forming single-charged sodium ions. So that's where you generate them with sodium chloride. Getting rid of the double-charged calciums, the double-charged magnesiums, those are the main things, but also in the double and triple-charged ions. So strontium, barium, aluminum, iron, things like that. As far as monitoring, we want to make sure that we don't hardness calcium and magnesium, but it's actually the magnesium that comes out first. We make sure that it doesn't break. The great softeners will remove all of the cations or most of the cations, so that you don't have to worry about the cation anion scalants, such as calcium carbonate, calcium sulfate, magnesium sulfate, barium sulfate. Because removing the double charged cations, and you're converting them into sodium sulfate, sodium carbonate, and these don't scale. Monitor again online. Instruments can be used for total hardness, and you can verify the accuracy of the online with benchtop analytical equipment. So know that your scaling is effective if you go year after year and you have no scaling occurring in the RO unit. Fatness is typically the biggest problem or the most frequent problem that we see. So I'm talking about three different pretreatment technologies: media filtration, cartridge filtration, and filtration, ultrafiltration. For the media, there may just be two media per site sand. Usually it's on a bed of gravel. We're seeing here coarse and fine sand and anthracite, so this is a dual media. And the dual media filters are great, so the anthracite is ground fairly large, so it can remove larger particles, and sand is a finer grind, but it's denser, so when you backwash, the sand drops to the bottom, so it can pick up smaller particles. And sometimes you have a third medium with garnet, very, very dense, so when you backwash, it goes to the very bottom. And then you can filter out even particles in the garnet layer, and again, usually all on a bed of gravel. Filters, you'll have some sort of distribution system on the inlet, some sort of distribution system on the outlet. So common, the downflow would be the most common media filtration. What we want to monitor here is pressure drop, and prep is a function of flow rate. So at the same flow rate, we want to monitor the pressure drop, and if the pressure drop gets above a predetermined level, then we want to do a backwash. And to monitor the effectiveness of particle removal, we use turbidity in out, see how well particles are being removed, or RO units in particular as pretreatment. We can use silt density index, and we're going to go over that later in this program. So as far as pressure gauges, they could be just indicators like we see on the left, or they could be indicating controllers, indicate transmitters like we see on the right. And same thing for flow meters. Filtration, you may just call it a pre-filter, but this is common, usually 1 to 5 micron, with 5 micron being the most common. Sometimes you'll see 10 micron as well. The round or the melt blown, these are the most common cartridge we see. So this is usually the last treatment step by pressure pump, although there may be a chemical injection downstream of the cartridge filter. So like any other filter, we want to measure pressure drop and flow rate. So adding flow rate, we monitor the pressure drop, and when the pressure drop gets a certain level, then we're going to change out the cartridge filters. And particularly for warranty of RO membrane elements, we have to make sure that the SDI feeding the RO membrane elements is below what the manufacturer warrants. Then now, especially 5 to 10 years, this is becoming more and more common to put membrane filtration as treatment. So instead of multimedia filter, or even sometimes instead of clarifier and multimedia filter, then we put membrane filtration. And membrane filtration is either microfiltration or ultrafiltration. Ultrafiltration having smaller pores than microfiltration. So we're seeing here merged filtration modules. So merged means that they're vacuum driven. If you actually see the modules in pressure vessels like we see here, then that's called a pressurized filtration system. But everything when we're talking about filtration, we're going to look at pressure drops and flow rates. Specific to membrane filtration is a term called transmembrane pressure, which is the difference between the feed pressure and the filtrate or permeate pressure. It's common to use either one of those terms for the water that passes through. Let me call it either filtrate or permeate. So my transmembrane pressure, when the transmembrane pressure gets high, then we're, in addition to doing backwashes fairly frequently, it could be every 20 minutes to every hour or two, we're going to do chemically enhanced backwashes and occasionally chemical cleaning, CIP, cleaning in place. The thing to make sure is that we have good numbers for silt density index coming out of the membrane filtration. So let's just take a minute or two here on silt density index, SDI. After we've done everything that we're going to do, so all the treatment has been done, we head of the high pressure pump ordinarily. Then we're going to measure the fouling potential of this water. A 0.45 micron membrane filter that goes into a filter housing, we keep 30 psi, just a hair more than 2 bar of pressure all the time during the entire test. And we pressure regulator that we can so that we can make sure that we are at 30 psi the entire time, and an isolation. So this silt density index gives us a measurement of the fouling potential. It's a 15-minute test. The standard The spray manufacturers want a 15-minute test, and the SDI has to be less than 5. But in reality, you want an SDI less than 3. So here is a manual setup where moving is coming from a down cartridge filter. Here's your regulator. Here's a pressure indicator, so we can keep it at 30 psi or 2 bar. And here's housing, and the membrane filter is in this housing. Here's a graduated cylinder. So through the actual test, we don't have time to do that here. There you can buy automated SDIs where you just have to hook it up, put in the pad, and then push a button and come back 15 minutes later. Today's world really measures the effectiveness of your fouling control. So we can talk about a lot of different things, but in the world, if you can consistently get SDI of less than 3 out of your pretreatment system, then we're going to say that pretreatment system is adequate. Doesn't mean that you won't have any problems with the RO unit, but say that the pretreatment system is good, SDI of less than 3. And then chemical attack control. There are 3 common ways. 2 more common: activated carbon, sulfite injection, and then a newer one, I don't see it as much, is ultraviolet irradiation. So activated carbon, just like in a media filter, it's a bed. So it's going to have the inlet piping, it's going to have the outlet piping, and we're going to be measuring pressure drop and flow rate, just like any media bed. Same thing would be true for softener, multi-filter, activated carbon. Anything that has media in it, then we're going to measure pressure drop and flow rate. But since activated carbon is chemical attack control, which is chlorine, but any oxidizing agent can destroy the polyamide membrane. So we want to measure either total chlorine or measure the oxidation reduction. Oxidizing water wants to take electrons, so the oxidizers like chlorine take electrons from molecules in the RO membrane that we need. When the oxidizing agent take those electrons, it breaks the bonds, and now the RO membrane can't reject as well. So an oxidation reduction potentiometer or a meter measures whether a water is oxidizing, wants to take electrons, or it's reducing, it wants to give away electrons. Well, a compound that wants to give away electrons is called a reducing agent. And sulfite is one of the most common. So SO3 - 2, that's the actual reducing agent. How you get your sulfite anion, negatively charged ion, is up to you. You can use sodium sulfite, sodium metabisulfite. There are 5 or 6 different chemicals that you can use, but sodium sulfite and sodium metabisulfite being the most common. So monitor to make sure that your sulfite injection is proper. Then we want to have 0 total chlorine going into the RO unit, and we want the oxidation reduction potential to be below a set amount. And that periodically you measure in the concentrate stream of our unit. We just want to make sure that we get the minimum amount of overfeed. As if you overfeed sulfite, you can also increase the biofouling in the unit. So last one, UV dechlorination. There are certain wavelengths that can break up the bonds in your chlorine compounds. So common to use a 254 nanometer lamp, low pressure or medium pressure lamp. You can dechlorinate. You can remove the clouds. You can destroy them with UV. Not as common. It's a newer technology. Not as common as the activated carbon and sulfite injection. And see a picture here of a UV unit ahead of a an RO unit and is there for dechlorination. So monitor UV dechlorination. Again, we want to make sure that we have zero total chlorine and the oxidation potential is below a predetermined set point. So we use handheld and on-stream instruments both for the total chlorine. We want zero total chlorine. That way we know that we're not going to get any trouble. We also recommend that occasionally you check the concentrate total chlorine. Everybody checks the total chlorine in the feed water if they have chlorine upstream. But it's not common to check the total chlorine on the concentrate, but a good idea. Because say you have a 75% recovery RO unit, that means your feed water is concentrated 4 times. So if you're doing 0.02 milliliter of total chlorine in the feed water, it's really tough to tell, is that zero or not? Well, you periodically check it in the concentrate stream. If you get 0.02 in the feed and 0.02 in the concentrate, okay, you really didn't have 0.02. But if you have 0.02 in the feed and you have 0.08 in the concentrate, then that would indicate that you really didn't have complete dechlorination and it has been concentrated in the RO unit. And would let, after a year and a half, 2 years or so, you'd up the membrane there in that last element and have to replace it. So again, ORP measures whether water is reducing or oxidizing, and the oxidizing water damages RO units. So that we have both handheld and on-stream instruments for ORP measure. This is monitor where you're going to have an effective chemical control system, pretreatment system. Well, you go year after year after year, and you see any oxidation damage of the membrane. If you have no oxidizers in the feed water, then you should not have damaged membrane. So, and say total chlorine of 0, just in case you do have iron rust particles in the water, because even amounts of chlorine in the presence of iron can burn out the membrane pretty quickly. So, summary and conclusion, we looked at the common pretreatment ways plus the monitoring of these ways for seeing control. No acid injection, scale inhibitor injection, and softening. We did the same thing for fouling control. We looked at 3 common pretreatments to control fouling in an RO unit. We looked at medial filtration, cartridge filtration, and microfiltration and ultrafiltration. And then finally we ended up with 3 common ways today for oxidizing agents to prevent chemical attack of the membrane, and that was activated carbon, sulfite injection, and ultraviolet irradiance. So thank you very much, and we'll open this up to questions.
All right, I'm just going to take the presenter bar back real quick, and our contact information available on the screen for anybody who needs to get a hold of either one of us. There are some questions that have come in, and the first question that has come in is, how common is organic fouling, and what should we do to control it?
Fouling rarely occurs by itself. It is common. Say common if we have lots of element autopsies, RO membrane element autopsies, and very common elements that are sent in, maybe 70%, maybe higher, organic fouling and or biofouling. It's hard to separate the two. Organic fouling, there have been some research that shows that the membrane actually has to be conditioned by certain organics, humic acids, prior to biofouling occurring, but there are a few autopsies where we could say, okay, it's cationic polymer fouling, so that would be strictly an organic fouling, and that we don't see anything else. But it's most of the time say, okay, we have organic fouling because we're scraping off all of this bio slime. We would just call it biofouling. But to answer the question, yes, organic fouling is common. No cheap way to remove organics in the feed water. Probably just to keep this short, so we don't spend an hour just on this question. To keep it short, or in the water, it's in your raw water. But if there's any way that you don't chlorinate it and then dechlorinate it, that will minimize the organic and biofouling in the RO system.
Okay, thank you. Next question is, what is a good sulfite concentration to target after dechlorination?
I recommend like a half to no more than 1 part per million of excess sulfite. Because sulfite also removes oxygen, so it'll get out your oxidizing agents first, and then it'll go after your lower level oxidizing agents like oxygen, so it oxygenates, makes your water anaerobic, and is conducive then to more of the slime-forming anaerobic bacteria.
Okay. How often should a multimedia filter be backwashed?
To answer that question, you really have to do some work. It's entirely a function of the feed water. So if you were on a surface water source, for example, it rains one day, well, you're going to have a lot more particles the next day as the rain, comes up. The water puts dirt, silt, clays into the water. So your backwashing would have to be increased during bad times. And then, later if the sun's out and the water clears up, then you don't have to backwash as often. So I mentioned in this webinar, you check pressure drop, and certainly when you hit a certain pressure drop, which usually is more than 15 psi or 1 bar of increase from when it was clean, then you would do a wash.
Next question here. If cleaning is required every 2.5 years on our system based on our DP and feed pressure rise, would it be better practice to clean every year as preventative maintenance?
Our motto at David H. Paul Inc. is if it's not broken, don't fix it. So our standard is if you get 3 to 5 years of life. Now this is on an industrial application, not a municipal drinking water application. So I'm specifically addressing industrial applications. If you do 3 to 5 years of life and don't have to clean more than 4, 5, 6 times a year, it isn't broken. Don't fix it. So the people in the audience are probably drooling over you being able to go 2 years without having to clean. That's phenomenal. So our recommendation would be no, not to clean every year, but we have very strict guidelines that we want the system cleaned when the normalized permeate drops no more than 15%, or the drop across any stage rises no more than 25%.
Is a zeolite media a better filter than a multimedia in terms of reducing turbidity and flow rate per cubic feet?
It's all based on particle size, the granules. So ion exchange resin beads are very small, 16th to 32nd of an inch. So it depends on whether you have anthracite, sand, and garnet. But a softener with resin beads is a good filter. filter, so long as the flow rates are in a reasonable range. So I think that's about all I can say is the softener is a good filter. If you compare it to a multimedia filter, we would have to know more about the granule size and what you actually have in the media filter.
A couple more here. Are there other scale-forming compounds besides polyometric silica that are not affected after softening?
Basically the answer is no, because your scales are cation, double-charged cations associated with double-charged anions. So calcium plus 2, carbonate minus 2, calcium plus 2, sulfate minus 2. And the softener is going to remove most, they're going to move down to a good level that's not going to hurt us. Remove the double-charged like the magnesium. Basically, it's the polymeric silica that's left.
Okay, more here. What is the best pretreatment to remove cationic polymers?
Cationic polymer can be a problem. The best pretreatment is not to add it. Always a risk of overfeed. If a softener and cartridge filter, then that's going to remove some. There's not an excellent way of doing that. That's common. So the absolute best advice is if you can get away with not injecting a cationic polymer in an RO membrane system, that's the best for two reasons. One, certain cationic polymers, when they mix with certain anionic scale inhibitors, and all of your scale inhibitors are anionic, negatively charged. So if you have a positively charged polymer that has a certain type of anionic polymer, they can come together and just form kind of a slime on your filters and on the lead end of your first membrane element. Also, the RO membrane itself is anionic. It's just charged as anionic, negatively charged. So if you have an overfeed of cationic polymer, it can bind directly.
Okay. Our last question for the day is, my pretreatment is a multimedia filter and I use city potable water as my source. Is that MMF doing that much for me, or is there a better use for the vessel seeing that I use city water?
It's a great question, and a lot of people think, well, wow, the city has gone through a clarifier, they've gone through probably slow sand filtration, they might could media filtration, dual media or multimedia filtration, but at least sand filtration. So would I need to put in a multimedia filter? Well, because you're getting the water directly from the tank, from that water treatment plant, you may be 5, 10 kilometers, 20 kilometers away from that. If a main breaks and repairing its sand gets to the piping, then when they repair that break and put it back into service, then that sand is going to come down to your plant. In today's world, most cities are using surface water. Not all, but a majority of drinking plants are on surface waters, and there's going to be organics in that surface water source. You get organics. If you chlorinate it, if you strictly free chlorinate it, then you form too many cancer-causing agents. So in today's world, most of these are using chloramines plus ammonia. It's not as good a biocide as free chlorine. So we actually get a biofilm over all piping. So that biofilm, depending on starts and stops and shake-ups and broken pipes, can be shaken off, and now you have pieces of biofilm coming your way. So it's a good idea to that multimedia filter. It's very commonly the very first treatment step when the city drinking water comes into the plant.
Look, that is all of our questions for today. You guys have our contact information available to you right there. Feel free to contact us with any questions that you may have, and we just want to thank you for your time today. Have a wonderful rest of your day.